we're going to talk about the life cycle of high mass stars. High mass stars have an early life similar to that of the sun. There's a collapse of the material within the interstellar cloud that the star is being born within, and then that star is born on the main sequence. In order to create a larger mass star, you just have to have more material condensed into one space in order to create that larger mass star, as opposed to stars that are about the size of our sun. So once you get enough material collapsed and contracted and into a tiny space, and you have enough pressure, you can exceed a certain temperature where you can start fusing hydrogen into helium in the core, and then you ignite nuclear fusion, you have a star on the main sequence. Now, after the star is born, the process of their lifetimes, these stars progress through the stages of its lifetime much faster than the sun. They spend less than about 100 million years on the main sequence, these high mass stars. When I'm talking about high mass stars, I'm talking about stars that are about 8 times the sun's mass and larger. Okay, so we're collapsing from an interstellar cloud, we create the protostar, and then eventually we have our massive star, the O and B type stars. We've got our high mass star, and then the high mass star passes through a pulsating yellow giant stage before it turns into a red giant. Now, once these stars, these massive stars, reach their red giant phase, the core begins to fuse one element into another, creating elements as massive as iron all the way along our periodic table. Okay, so in stars like our sun, when we've run out of hydrogen to fuse into helium, then we can fuse helium into a carbon, and that's about all we can do because there's not enough pressure and a temperature to cause carbon to fuse into other things further along on the periodic table. But with these more massive stars, stars about 8 times the sun's mass and larger, these stars, when they're reach their red giant phase, okay, there's enough pressure and temperature, large enough temperature there for them to fuse carbon into other elements higher along on the periodic table to keep that star burning for just a little bit longer on its lifetime before it ends. But the more massive a star, the faster it's burning through all of its fuel. And when I'm talking about massive, I mean literally the mass of the star, not the size of the star. Now, in its fusion process, once the star has reached fusing other elements into iron and creating iron in its core, the core at that point has then run out of fuel and it collapses. So the star's heavy elements that it has created in its interior, everything up to iron at this point, are blown out into space along with its layers after it's finished fusing other elements into iron in its core. And when it explodes its outer layers into space, you create a supernova. And what's left over is a neutron star or a black hole. Stars that are about 40 times the sun's mass and larger are able to create black holes when they reach the end of their lifetimes. But stars of about 8 to 10 times the sun's mass to about 40 times the sun's mass are going to create neutron stars instead whenever they reach the end of their lifetime. So neutron stars are the collapsed core of one of these massive stars. These stars were originally 8 to 20 times more massive than our sun. Now, these neutron stars are supported against further collapse on themselves because of their immense gravity due to neutron degeneracy pressure. That's similar to our electron degeneracy pressure that we saw in the white dwarf. So now in neutron stars, we have even more gravitational force there, way more mass that's trying to be condensed into a very tiny space. So now we've got a bunch of neutrons that are making up this star, not necessarily electrons. And those neutrons also, you can't have more than one neutron occupying the same space. And so those neutrons are going to want to push or repel away from each other. So you've got a gravitational force pulling everything together, and that's being supported by this neutron degeneracy pressure. And this neutron star shrinks to about 20 kilometers across, about the size of a city, with so much mass. And then these things are spinning very, very, very rapidly. Now, about 10% of all neutron stars are what we call magnetars. Magnetars are an exotic type of neutron star, and as you might expect, they have a lot of magnetism. So here's an example, an artist's rendition of a magnetar. So we've got our neutron star here, which has an incredible amount of magnetism. We've got our magnetic field surrounding it here, and this one is shooting off beams of material from its poles, jets of material from its poles. Now, magnetars can have flares, just like our sun has flares, solar flares. And one flare from a magnetar can be trillions of times stronger than that of the flares from our own sun. And these events are quite extreme, and then they can, their effects can be felt throughout a large portion of the Milky Way, actually. Now, pulsars are another type of neutron star. They are neutron stars that emit pulses of energy observed in multiple wavelengths of light, many wavelengths of light. You could see them pulse in their energy in visible. You can also see it in the X-ray. You can see it in the radio wave part of the electromagnetic spectrum. These neutron stars are also spinning rapidly, and they have magnetic fields, although not as intense as the magnetars. And then they can launch twin beams of energy from the star's poles. And you can think about, that star is spinning, it's got these beams of energy. Think of those beams of energy shooting out from the poles as being like a lighthouse. Whenever the lens of the lighthouse swings around, you get that pulse of light, comes around again, you get the pulse of light. Okay, and the rotation of these bodies, of these pulsars, is very stable, very constant. And so you get this lighthouse effect of those jets of material spinning around from the pulsar, and that's that pulse of energy that you see. And those pulses of energy are the most accurate clocks. They're even better than atomic clocks at keeping time. And in fact, some atomic clocks will be calibrated based on pulsars. This image is of a pulsar at the center of a nebula called the Crab Nebula, which is actually a supernova remnant. We'll see the Crab Nebula here in a minute. Now, this is a false color image. We've got optical data, visible wavelengths of light from Hubble, shown here in red, from the Hubble Space Telescope. And in blue, we have X-ray wavelengths of light taken by an observation from the Chandra Space Telescope, okay? So in the middle here again, we've got the pulsar. It's got beams of material shooting out, and we've got this disk of material sort of swirling around. Let's recap the life cycle of these massive stars. They're all born in the same way as the sun, just with more material surrounding them. And then they are born onto the main sequence as these large O and B type stars that appear to be a bluish color. And then those stars will fuse hydrogen into helium in their core for a much, much shorter period of time than stars like our sun. Eventually, they'll fuse hydrogen into helium. Once they're run out of hydrogen, they'll start fusing helium into carbon, and then they'll fuse carbon into other things higher along on the periodic table until they get to iron. And once they finish converting other elements into iron, then they'll expel their outer shells in a very large explosion called a supernova. And then left over will be a neutron star. And stars that are even more massive than that, the most massive of the massive stars, will also end their lives as supernova, but then they'll be left over with a black hole in the middle. Now here is one of the most beautiful supernova, in my opinion. This is one of my favorite images of space. And this is called Cassiopeia A. It is a supernova remnant, and it's also a false color image. And don't remember exactly which colors are which, but I do know that the yellow here is visible wavelengths of light taken from the Hubble Space Telescope, Here's the Crab Nebula, also a supernova remnant. Remember the Crab Pulsar that we saw earlier? That pulsar is in the middle of this nebula that we're calling it. It's a supernova remnant. It's called the Crab Nebula because the first person who observed it in the optical wavelengths of light, that's visible wavelengths of light. This image that that person drew, because this is before photographic plates, looked like a little bit like a horseshoe crab. But today, this is what it looks like in a false color image. And I think it looks a little bit like a geode or a sponge. You've got these filaments in here where there's more material packed in to these little tiny spaces, long lines, and then you have regions where the material is less dense and there's less material there and it's easy to see through. It's what we call optically thin. And all of these supernovas are going to be expanding forever. They're going to be expanding and expanding outward. So if you could hitch a ride on the edge of these expanding clouds here of the supernova, you would be moving really, really fast. And here's another supernova remnant. This one's called Supernova 1987A. This one's really cool because over the course of 1994 to 2003, we see that there's this ring of material surrounding the central neutron star here. And that ring of material that you're seeing here is changing still over time. This is called like a string of pearls, and these string of pearls are lighting up and changing shape over time. And actually, that's the zoom in on the middle part of the supernova remnant. And this is the zoom back, the full supernova remnant, and we've got two rings, kind of like an hourglass shape, and then the neutron star in the middle here. So this is the image that we see in space looking at it. But if you were to kind of turn that image on its side, this is sort of an artist's rendition of what this supernova actually looks like in space if we could rotate around on its side. And it's actually kind of like an hourglass shape. We've got material up here and up here, but if you change your perspective and look at it kind of down the axis of the hourglass, then you would see these two rings stacked up kind of like this. And so what they think happened is that you had the star here, but the original star was also surrounded by a disk of material, and when the star exploded into its supernova, that material that was expelled from the star kind of smashed up and banged into that disk of material that was originally surrounding the star. And then that material is still moving outward and impacting this ring of material surrounding the star. And that's what's causing the changes in this ring of material that we're seeing around the supernova remnant.